able to discuss the discussion I had with my son, about those Legos. That's number one. Number two, it's to get in the idea of probability and what that means. And number three, it was the idea of explaining a classic mathematical problem that all of this is related to. That's the least important of the three. The two most important is, number one, if I can give you a tool that you can help explain to your kids someday, that's great. Number two, the basis of probability is the most important thing for me. Understanding how we can answer this question in the simplest possible way. So here's the number. I just flash?
Yeah.
Okay, good. I'm not just seeing things anymore anyway. So, number of rolls until we see a repeat. Okay, so if you can see, this is rolling a die. No disrespect intended here. We'll put that back up. I very often ask people, and I want to parallel some talking here. If you roll a die, what is the chance that you roll a 1? The number 1 on a normal six-sided die. What is the chance? So I hear 1 out of 6, 1 out of 6, 1 out of 6. I'm hearing lots of 1 out of 6s. So we're fairly okay with that. Okay, good. I'm going to put that over on the sideboard for a second. So if you roll a six-sided fair die, the probability. I'm going to show you guys a little bit of mathematical notation here, statistical notation. Don't get freaked out by it. It doesn't mean anything except shorthand. Probability of rolling a 1 is 1 in 6. I want to deconstruct that statement right now with you guys. Okay, I want to deconstruct that statement with some color, which is in my pocket now. So when you see, we're going to use this notation over the next couple of days, or our last couple of days together. It saves us the shorthand of having to constantly write probability of ... So the little p outside, sorry friends, I mean to drag it out like that. It just means probability of something. Now what is the something? The something is in parentheses. Those of you that have Math 111, this is not function notation. I know Sam's thinking like, oh my god, I hated this part of Math 111. It's okay, it's not that. It's just shorthand. What goes inside here is the description of what in probability is called an event. It's called an event. And all that is it's the result of an experiment. If you throw a die, you know all the possible events, don't you? You know all the possible events. The events are
1 through 6.
1, 2, 3, 4, 5, or 6, assuming that you have a fair die. Assuming that you have a fair die. You know what? While we're talking about this, everybody just hand this around and grab a die. Just to have a model in front of you so you can actually play with this a little bit. Because I want to tie theory to practice throughout the rest of the 3 days we have together. Because that really, honestly, theoretical probability is great, but data collection probability is way more telling. As I've seen. This is how I explain it to Max. This is how you can explain probability to a 6-year-old. By just generating data. Me and him flip coins all the time. Let's play. Heads beats tails. I'm like, okay. And we played. And at the end, he's like, we both won the same number of times. I'm like, well, okay. And we let that sit. A couple days later, we play again. We tied again. Well, oh, I got 16, you got 15. I'm like, well. And over the discussion, the data begins to explain what 1 and 2 means. Or 1-to-1 odds mean. And that's the idea. If you can collect data enough and see patterns, it's amazing what it can uncover for you. Or what it can disprove for you too, which is also kind of fun. So anyway, we have this notation, the probability of rolling a 1. Okay? Now you all said 1 and 6. I shouldn't say you all said. Those who voted said 1 and 6. How many agree with it? How many disagree with it? How many are not sure? That's okay too. Good. Good. I like that very much. Okay, those of you that are sure it's 1 and 6, prove it to me.
Well, you only get 1 roll.
You get 1 roll. Max just rolled a 1. Grant? 5. 2. 5. 5. 2. 1.
7.
Okay, wait, hang on a second. I got an easier solution. Everybody grab a die, 1 die. Roll it right now. Okay, hang on a second. Don't tell me what you got yet. There's almost exactly 30 people in the room. That's fantastic. Raise your hand.
Yeah, not everybody has dice. I don't.
Yeah.
Oh, how do I start over here and get back here?
Yeah, I don't know.
It's a network
Fair
problem.
enough.
This is great. This is how government works. We're on DSL in this room. Freaking awesome. Anybody still need to die? We have served the community. There we go.
I don't want to die.
Grab it. Grab a die. Roll it once. Unless you don't want to die. Explaining that to my 6-year-old has been the hardest thing. Why is it called die? Okay, raise your hand if you got a 1. 1, 2, 3, 4, 5. Okay, so I'm going to keep quick data over here. You guys don't write this down. Okay, 1, N. Okay, so 1 and then N. I'll explain that in a second. Sorry, hands if you got 1 again, that time?
5.
5, okay. And did everybody roll in the room? Everybody in the room roll? Yes. 5, 31. Do it again. Grab the die, roll again. Raise hands if you got a 1. Raise hands if you got a 1. 1, 2, 3, 4, 5, 6.
You got a 3.
Do it again. Do it again. What you are doing right now, FYI, is you are doing what your TI does in the points program, but you're actually doing it. The TI does it automatically very quickly. We're doing it slow because there's a point I want to make here. Raise your hands if you got a 1 that time. 1, 2, 3, 4, 5. Okay. 5,
So the 31 is just number of rolls.
Roll again. 31 is how many people are rolling each time. 30 people in the room. That's why I asked. That's why I counted. Raise your hand if you got a 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Do it again. Couple more times. Couple more times. Couple more times. Hands if you got a 1. Hands if you got a 1. 1, 2, 3, 4, 5, 6. I heard a very adorable comment. I don't like this die. I like that comment a couple back. That was adorable. I love that. Roll again. Hands if you got 1. 3, 4, 5, 6, and 31. Do it again. Comments down, bossy.
I broke it.
Do it. Hands if you got 1.
She broke that.
Has anybody not gotten the 1 yet? Has anybody not got the 1 yet? Okay, hold that thought. Hold that. Well, Matt, you got the very first one. We didn't count it, didn't we? Hold that thought, though. We're going to come back to that. That ties back to the Excel thing that we looked at over here. You'll see that. Roll again. Once. Okay, do it again. Let's do a couple more times.
Mine's broken.
Yours is broken. Hold that thought.
Mine is 2.
Once. 1, 2, 3. Do it again. Get fellas, I'm sorry. Once. 1, 2, 3. Do it one more time. We can do this indefinitely. But I think you're getting the point. Hands, you got a 1. Yes.
Not a 1 in 16.
Hold that thought. Oh, I love what I just heard. I just heard that is not a 1 in 6 yet. Who did not get 1 any time during those 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 rolls? Who didn't get 1s at all? A few of you didn't. Notice the hands up. 5 people. Roughly 5 in 31. Roughly 5 in 31 people. What percentage is that? That's about 1 in 6, isn't it? Now think about this. Come over to here. We had you guys roll 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 times. Some of you didn't see 1s. You probably saw everything else. Maybe you missed a couple numbers, but you weren't looking for those numbers. Look at this graph you guys made right here. Remember how far this thing went out? This was the number of times you had to roll a die until you saw each of the faces at least 1 time. That means you guys still wouldn't be done. You guys that didn't roll a 1 yet would still have to be, there's 11 right there. Look how much more there is. And look how many people had to roll past 11 to get to it. So those of you that got 1, did you notice? You might not have noticed. Did you notice that there were some numbers you didn't get? Like maybe you didn't get a 6, or you didn't get a 4. You weren't paying close attention to it because you're paying attention for the 1. But you see, the idea is, it takes a while when you're rolling a die to actually get all the faces, 1 or otherwise. So when you say your die is broken, I love that. I hate the die is broken, 1 in 6 chance my butt, or something along those lines. All those statements are wonderful, but they also owe to the fact that as human beings, we don't understand randomness very well. We think that a 1 in 6 chance means what?
Roll 6 times.
For every 6 times you roll a die, it's going to happen once. Not necessarily, because, let's refer back to the other graph. If that was what it meant, which one of those bars should be the biggest?
6, 7.
7.
Let's think about that. If a 1 in 6 chance meant, it's okay. If a 1 in 6 chance meant that out of every 6 rolls, you get exactly 1, 1. Can we extend that to all the numbers? Because that would mean that out of every 6 rolls, we get exactly 1, 2, and exactly 1, 3, and exactly 1, 4, and exactly 1, 5, and exactly 1, 6. So what should be the tallest bar?
7.
Shouldn't 6 be the tallest bar? Because we would get every one of them until, excuse me, yes, 7. Because you get every one and then you get a repeat on the 7, sorry. But 7 is the shortest bar. So how can a 1 in 6 chance mean that every 6 rolls, you get every single number exactly 1 time? It doesn't seem like it can mean that, right? It seems like 7 should be the tallest if that's the case, but 7 is actually the smallest of them. Now, is that because our data is screwed up? Do we get screwy data? Well, let's take a look. What I did in the office yesterday was I created a theoretical versus actual. So what this is, the green bars in the back there are your guys' data. The pink bars, excuse me, the green bars are the theoretical. The pink bars in the front are your guys' data. So it's a little hard to see because it's a 3D graph, but you see the shape of your data? How does it compare to the shape of the green data behind it? It almost looks exactly the same, doesn't it? Which means your data was not screwy. Your data actually, the graph you guys got is exactly what it's supposed to look like, theoretically. Which means you were rolling really well, really randomly. But this allows for all those goofy clumps. When you actually look at the individual data in there, it's actually pretty noisy. It's pretty noisy within each of your results. But that's okay. That's why you have to collect more data. That was the point of me flipping the coin and getting tails 9 times in a row. Well, that's okay, but that's a deviant result. Let's flip more and see how that plays in with all of it. Let's take a look. I did this for both of you guys. I also did the theoretical for the all faces, okay? A little bit noisier. Here's your guys' results up front in red, and behind it is the green. Can you see the green back there? Let me tilt it a little more. If you have a hard time seeing that, let me tilt it some more. 3D rotation. Let's see. I think the Z is what I want to mess with. Or let me see if it's the Y. Oh, nope. Here we go. Much. Is that better?
Yeah.
Ish. Ah!
Whoa.
Sorry.
That works.
Crap. Undo. Undo. Well, you can see the point. The point is, although our data is fairly lumpy, like we're too short on 10, our shape overall is pretty good compared to what should have happened. Is that fair enough? Ish. Now, I want to come back to this as well, but not right now. Let's undo all that goodness and come back to there. I want to come back over here to what this 1 in 6 means, because that's what I want to continue that discussion right now.